Hello everyone, and welcome to We Meet at Digital Days. My name is Marie-Therese Kohl, and I will moderate this presentation. We are very pleased that you took the time to participate in our virtual conference. The topic of this presentation is Antennas, Radiation Pattern, and the Anechoic Chamber, a Win-Win. Our speaker is Ashiro Shen. He will hold the presentation and will answer your questions. But before we start, I would like to point out one thing. You will be muted during this presentation. This means that you cannot ask questions via microphone during the presentation. But nevertheless, you have the opportunity to ask questions during the presentation at any time via the chat function. And you can find the chat function in the control panel. The presentation will be about 30 minutes long. The chat questions will be answered in a Q&A session following the webinar. There are 5 to 10 minutes in addition scheduled for this. If we are unable to answer all your questions within this time, we will answer them via email afterwards. And if you still have any other questions left, just mail us at exhibition@we-online.com and we will try to answer our questions promptly. At the end of the webinar, you will be asked to participate in a feedback survey. We would be pleased if you take the time to fill out the survey and help us to improve the event. After this session, you will receive the link to the presentation and the recording will be available at our website shortly. But now I will hand over to our speaker, Ashiro, and I wish you an exciting presentation.
Hi, thank you, Marie, for the introduction. Welcome and thanks for attending this webinar today. My name is Ashiro Chen, as Marie said, and I'm product manager for Würth Elektronik. And today I will be holding this webinar titled Antennas, Radiation Pattern, and the Anechoic Chamber. The aim of this webinar is to explain why an anechoic chamber is necessary to characterize the performance of an RF antenna and what's the process before going into the chamber, like the antenna matching. Later on, we will check the results of these measurements. Here you have the agenda for today. We will be introducing the IoT antennas and the ones that we have in our portfolio. Then we will jump into the anechoic chamber to explain why an antenna needs to be measured inside under certain conditions. We will comment our newest collaboration with the University of Valencia, located in Spain, for the use of its anechoic chamber. Finally, we will go through the results and data obtained from the far-field measurements in the chamber. And later on, I will be answering your questions. Internet of Things, or IoT, it's a summarizing term for the next generation of smart devices that can transmit or receive data over a network autonomously. IoT devices and the data they generate provide us much needed connectivity for a range of new applications. The development of an antennas has been invaluable in the progression of wireless technologies and their ever-increasing use in IoT application. The miniaturization is one of the biggest challenges for the optimal antenna performance. We can differentiate main antenna topologies for IoT, the wire antennas, which are not the best in terms of needed space. Then we have the trace antennas or PCB antennas and the chip antennas, which sometimes they need a matching to work with the best performance. In this webinar, we will be talking about the last ones, the chip antennas. So we have in our portfolio match code, which is called MCA. So they are multi-layer ceramic antennas and are manufactured using LTCC, low temperature co-fired ceramics technology. Each dielectric layer has pattern metallization on the surface and connects the other layers through vias. The layers and vias together form a helical pattern multi-layer antenna. As you can see in the picture below, these multi-layer chip antennas are very small in size, easy to tune, that's referring the antenna matching, and they have excellent size to performance ratio. They can work in different range of frequencies for different RF applications, such as GSM, Wi-Fi, or 4G. The working principle is that they work adapting a signal from a circuit to free space radiation and vice versa. Recently, we have added some new antennas into this family, into the MCA family, and they can also work in different frequency ranges depending on the application. Due to the inner construction of these new antennas, they require less ground clearance. Some of them can even work in a dual band, and they are omnidirectional or quasi-omnidirectional. All of them are easy to integrate in the PCB. Here we can see some of the most important protocols and standards as a reference and the frequency ranges they work. These antennas have been specially designed to work out those frequencies. As you can see, for example, in the Wi-Fi, you can see two main frequencies where the Wi-Fi works, and that's why sometimes a dual band antenna is needed. Now we will be explaining two of the most important parameters of an antenna. First of all, the radiation pattern, which is a term related to the antennas and is a graphical representation of the properties in free space, represented both in vertical and horizontal polarization with an axis as a reference. In this case, we will take the floor normally as a reference. The gain of an antenna describes the efficiency converting the input power into electromagnetic radiation in a specific direction. The MCA antennas are omnidirectional antennas. As you can see in the picture here below from a simulation. That means that they have anisotropical radiation properties, which means that they can radiate in all the direction, and the pattern has low changes with the modification of the direction. For the old, we can say, antennas that we have in our portfolio, the radiation patterns are already available, so you can check them in the datasheets. And for these new ones, they will be soon available with the new setup and chamber we will be commenting and showing in a moment. The gain and the radiation pattern are related to the far field measurements, and they are measured in a special room, which is called Anechoic Chamber or RF Anechoic Chamber. So what is an anechoic chamber? It's a closed room which was specially designed to absorb all the reflections and avoid any external electromagnetic noise that could be caused by any electronic equipment. Therefore, we can characterize and obtain the performance of the antenna and its properties. In particular, the gain and the radiation pattern that we have just commented. In this sketch here below, we can differentiate the main important parts of the anechoic chamber. On the left side, we have the transmitter, where the antenna is placed, the antenna underthrust, and it can rotate in the azimuth. The azimuth is parallel to the floor, 360 degrees. Then on the other side, we've got the receiver, which will register all the radiation of the antenna. Thanks to all the absorbing material in the whole chamber, we will be absorbing the rest of the reflections. An anechoic chamber is needed to characterize the performance of an antenna. At this point, I would like to comment that Würth Elektronik has signed a new agreement with the University of Valencia, which is located in Spain, for the use of their anechoic chamber, which is located in the Superior Engineering School in Valencia, inside the university. This is a well-equipped chamber and one of the biggest in Spain. The radiation pattern can be obtained in 360 degrees, so rotating the azimuth axis, as we said, and we can get the copolar and cross-polar planes. It is capable of performing far-field and near-field measurements. Thanks to this collaboration, we have been able to implement a new setup for the new antennas inside our portfolio. Later on, we will go through these results. But before going into the antenna matching, I would like to comment some important concepts that have to be understood. One important key concept is the impedance, which we can say is the opposition to the smooth flow of energy. It is measured in ohms, and it is a complex value which varies with the frequency. That's important because as the frequency increases, the wavelength decreases until some point where it is 10 times smaller than the length of the line. Then it's what we call transmission line, and at this point, the impedance matching becomes necessary. The maximum power is delivered to the load when the source and the load impedances are complex conjugates of each other. For example, resistances should be equal and the reactances must be equal in magnitude but opposite in signs. Here at the top right, we can see that the impedance is formed with a real or resistive part and imaginary or reactive part. I would also comment that in DC or low frequency systems, the reactances are so small that they can be ignored. Next concept, it's the VSWR, which describes how well the antenna is impedance matched to the transmission line where it is connected. It is a numerically measurement, therefore it has no units, and this will directly affect the transmitted power, as you can observe in the table. Depending on the return losses, we will have a different relation. The ideal value would be 1, but in real life, a value between 1 and 2 would be a desirable value. So the lower the VSWR, the better the power transfer we will have. That means that we have a good matching in the antenna. Related to the last parameter are the S parameters. These parameters help in quantifying the input and the output power. They are critical for an RF design, and they are measured for all the RF components that we offer in our portfolio. We will focus in a concept of the S parameters, which is the S11, or so-called return loss, because it's one of the parameters that is measured for the antennas using one port in the equipment. For example, a vector network analyzer, a VNA. It is expressed as a negative value, as you can see in the example graph on the right side. As I said, for the antennas, which are single-ended components, we measure the return loss to check the antenna mismatch. A large mismatch produces a large S11, and a very low S11 at our desired frequency band almost guarantees our perfect operation of the antenna. I said low because it's a negative value. I would also like to say that the S parameters are available in our website to be downloaded. Okay, so now we can jump into the antenna matching and its importance for the antennas. Antenna matching is one of the most difficult work for an RF engineer, and it requires a large expertise in RF and electromagnetics. Antenna matching, as a definition, is a process that consists in the design of the antenna's input impedance to match the corresponding RF circuitry's output impedance. In most cases, you will see that the value of 50 ohm is used. The performance of the antenna is affected by its surroundings. So that means any change in the antenna's immediate environment changes its input impedance, which in turn changes its operating frequency. And therefore, we would need a different antenna matching. Smith chart, you can see here on the right side, It's the best for the process. Making use of it, we can get the matching of the antenna. The goal in this case is to move the impedance at the antenna operating frequency to the center of the Smith chart, where we have the 50 ohm. This can be achieved using RF inductors and/or capacitors. Once a measurement is made, it appears on the Smith chart as a complex impedance with resistive and reactive components, and then we will be able to do the antenna matching. This is a really complex process, and for more details, I would like to invite you to check our existing webinar in YouTube, which is totally focused in the antenna matching, or our application note number 57, which is titled MCA Multilayer Chip Antenna Placement and Matching. Here you will be able to check all the details. The important for today is to know that a good matching is a must if we want to have the best performance of an antenna. As we said, to characterize it and check it, we make use of the anechoic chamber. Here you can see an example of the different performance in an antenna using matching or not using it. The graph above is from an antenna without any matching, and the graph below is from an antenna where the matching circuit has been done. You can see that the frequency point could even vary, and in this case, the return loss has a difference of more than 50 or minus 15 dB at the resonance point. In this case, 2.45 for a Wi-Fi antenna. At this point, I would also like to comment that the antenna matching is a service we offer to our customers. It has no cost for the MCA antennas, our antennas, no matter where antenna is placed in any PCB. For more information, you can contact this email address and ask for details and more information about it. Don't worry, because later on you will receive this presentation, so you can check the email again. Okay, now we will be talking about the test setup used for the measurement in the chamber of the antennas. Here we take a closer look of the antenna. This is a PCB. On the left side, you can see the antenna, and next to it, the matching that has been made for this antenna. We can also see an SMA connector. This is because we need to connect the antenna to the transmitter in the anechoic chamber and to place it at the positioner. Therefore, we've prepared this PCB. The return loss, the S11, as we commented, can be also obtained to check that it radiates at the frequency of interest and that the matching has been properly done. On the left side in this picture, you can see a closer look of the anechoic chamber with the positioner, where it is also the transmitter where we place the PCB on the top. You can see it on the right side. If we zoom in, at the top, you can see the PCB where it's placed with a special fixture for the purpose. The positioner on the left can rotate in 360 degrees. That means we can get the whole radiation pattern, and in the azimuth axis. In this case, the azimuth is parallel to the floor. And then we have another axis, which is located at the PCB and can be rotated also in 360 degrees. In this case, we rotate it to measure one plane or another. We will be talking about the E plane and H plane in a moment. The speed can also be adjusted for the purpose of the positioner. And then on the other side of the chamber, we've got the receiver, which is an antenna that will register the emission of the transmitter, our antenna under test, and the antenna would like to characterize. Later on, we will be able to use the data to plot the radiation patterns, check the gain, and the performance of the antenna. This receiver can also be rotated to measure the copolarization or cross-polarization. as the transmitter. Of course, when the measurement is performed, the chamber is totally closed and nobody is inside. Before going into the results, I would like to comment one more key concept, which is the polarization of the antenna. We have two kinds of polarizations: the copolarization that you can see in this picture on the left side, and the cross polarization, which can be seen on the right side. Then we define also two planes, the E plane and then the H plane, which is, they are perpendicular between them. So depending on the orientation, we will have one on another plane measuring and then one on or another polarization. In this case, we can see that we have copolarization because both the transmitter and the receiver are polarized, are with the same polarization. Then on the right side, we can see that the PCB is still in horizontal, but we change the polarization of the receiver. That means we are measuring the cross polarization in the E plane. Then we've got the H plane. As you can see here, now we place the PCB in vertical, and then we as before, we rotate the receiver. On the left side, we have the copolarization, and the right side, it's wrong, sorry, but it should be the cross polarization. The receiver would be 90 degrees rotated to have the cross polarization, as before here with the E plane, but in this case we are measuring the H plane. Now we will have an overview of the real results. These diagrams correspond to one of the new antennas, the 748-896-0245, which work in the range of 2.4 to 2.5 gigahertz. All the diagrams show the rotation along the 360 degrees, and they are expressed in dB. I would like to comment that these patterns are not normalized. We will see the normalized patterns later on. Here we can see the H plane on the left side, and both the copolarization and the cross polarization. As you can see, we have around 30 dB difference between the copole and the cross pole, which means it is a really good antenna, because the cross pole in this case quantifies how much the antenna radiates in undesired directions. So normally what it's interested for us is the copolarization. As you can see on the left side, the copolarization, the differences between maximum and minimum are around 2-3 dBs, which in terms of an antenna, it's really low. And you can see the omnidirectional antenna here along the whole 360 degrees. Then in the E plane, we can also observe the copolarization, which is much better than the cross polarization, and the low difference in the copolarization around the whole 360 degrees. Again, here the interest is for us the copolarization, and we can check how the antenna is radiating in the all directions. Here, for better reading, we've normalized the diagrams. That's just dividing by the maximum values in each plot, and then we can see here easier the radiation pattern. Same for the E plane. Both values have been normalized. It means we have the 0 as a reference, and compared to an ideal isotropic antenna. So these were the results of our measurements. Of course, they will be they have been measured for all the antennas, and they will be available soon in our datasheets. So for the future, as I said, all the radiation patterns of these antennas will be added to the datasheets, because right now they are not available. And I would like to comment also that the chamber can be adapted for some other kind of measurements. Dielectric constant, antenna matching service, so for different antennas. With the antenna matching service that we offer. And one thing to point out is that just as the operating frequency of an antenna depends on its surroundings, as we said, the radiation pattern also changes, although less, but it depends on the PCB and the fixture where it's placed. That could lead to zeros in the radiation pattern that we would see in the diagrams, and could lead in a big losses for a specific channel. With channel, I mean direction. For this reason, we think it is important to offer on demand the radiation pattern characterization to our customers or the antenna matching. So we can offer both the antenna matching on the PCB, and then we can perform the measurements. For more details or questions, please contact these two emails or the email before regarding the antenna matching. So thanks for your time attending this webinar. And now I will be answering all your questions regarding this topic. Thank you.
Yes, thanks Ashiro to you for your interesting presentation. As you already mentioned, we would like now to turn our attention to your questions, so feel free to enter them in the questions window. But maybe we can already start with one, Ashiro. There's one question: what frequency ranges are covered by the anechoic chamber for testing antennas?
Sir, could you repeat? I couldn't hear the question.
Sure. What frequency ranges are covered by the anechoic chamber for testing antennas?
Okay, now the audio was better. Okay, good question. So basically, they can be measured in this chamber from 300 megahertz, and we can say up to infinite, so gigahertz. But with the setup and the equipment that we've got in the anechoic chamber, because outside the chamber we've got all the equipment to register the data, like a VNA, different equipments, we are able to measure up to 20 gigahertz in this case for our antennas. But we could measure up to higher in frequency with a different kind of equipment or better equipment.
Okay, cool. Thanks. Another question where I can see here, how can we access antenna matching service?
Okay, so the antenna matching service, as I said, you need to contact the email. It was in a slide before, but you will receive the presentation. And there you can provide us the details about the antenna, the PCB, where it's placed, and all the information about it. And then we will discuss the project with our RF experts. My colleague Ali or me, we can answer this.
Okay, cool. Thanks. Another question, what is the difference between 2D and 3D radiation patterns?
Okay, yeah, I guess the question is because in the slides I showed the 2D diagrams. So I showed the 2D diagrams because it's easier to read and to interpret the results. But the 3D patterns are basically the same. And what we did is to get the 2D patterns from the 3D patterns, just taking horizontal and vertical planes. And then we can get the 2D patterns that I just showed in the presentation. So that would be the differences. In the end, we've got the same information.
Okay, good to know. Thanks a lot for answering the questions. I would say if there are any questions left, we will answer them via email afterwards. So thank you very much for your attention, and I hope you enjoyed the presentation. For your information, the next presentation topic is Anticipate EMC with LT-Spice, and you can still register, so feel free to join here and enjoy our digital days. Goodbye.
Thank you. Bye.